Have you ever looked up at the night sky and wondered about the force that holds the moon in orbit around the Earth? Or the force that keeps our planet revolving around the sun? That force, my friends, is gravity. The invisible tie that binds the cosmos together. It's a force we experience every day, yet it holds profound mysteries. Gravity is responsible for the majestic dance of celestial objects, sculpting galaxies and igniting stars. Yet for a force that shapes the cosmos on such a grand scale, gravity is surprisingly weak. It's the weakest of the four fundamental forces that govern the universe, a fact that might surprise many. How can something so seemingly powerful also be the weakest? This intriguing paradox lies at the heart of our exploration into the nature of gravity. Join me as we unravel the mysteries of this fundamental force and discover why its weakness is not a limitation but a key to the universe's intricate design. To understand gravity's weakness, we must first introduce the cast of characters in our cosmic drama. The four fundamental forces. These forces, each with its own unique characteristics and strengths, govern the interactions of matter and energy at the most fundamental level. First, we have the strong nuclear force, the strongest of them all. This force is responsible for binding protons and neutrons together in the nucleus of an atom, overcoming their natural electromagnetic repulsion. Imagine the strong force as the glue that holds the very building blocks of matter together. Next, we encounter the electromagnetic force, familiar to us through everyday phenomena like electricity and magnetism. This force governs the interactions between charged particles, holding electrons in orbit around the nucleus and enabling the formation of molecules. Then, there's the weak nuclear force, responsible for certain types of radioactive decay. While less familiar, it plays a crucial role in processes like nuclear fusion within stars, the very furnaces that forge the elements essential for life. And finally, we arrive at gravity, the force we've come to know as the architect of the cosmos. Gravity governs the interactions between objects with mass, drawing them together across vast distances. These four forces, working in concert, orchestrate the symphony of the universe, from the smallest atoms to the largest galaxies. But as we delve deeper, we'll discover that gravity's role in this symphony is far more subtle than it first appears. The weakness of gravity becomes strikingly apparent when we compare it to the other fundamental forces. Let's take a simple example. Imagine holding a refrigerator magnet near a refrigerator. The tiny magnet, with its relatively weak electromagnetic force, can easily overcome the gravitational pull of the entire Earth, holding the magnet firmly in place. Consider the act of jumping. With a simple exertion of your muscles, you can temporarily defy Earth's gravitational pull. Yet, the amount of gravitational force you overcome is minuscule compared to the forces at play within your muscles at the atomic level. The disparity in strength between gravity and the other forces is staggering. The strong nuclear force, for example, is about 10 to the power of 38 times stronger than gravity. To put that into perspective, imagine trying to hold a feather against a hurricane-force wind. That's the kind of difference we're talking about. Gravity's weakness, far from being a cosmic oversight, is actually crucial for the universe as we know it. If gravity were much stronger, stars would burn out much faster, their intense gravity compressing them and accelerating nuclear fusion. The delicate balance of star formation, stellar lifetimes, and the creation of heavy elements would be disrupted, potentially making the universe a much less hospitable place for life. The vastness of space itself is also a testament to gravity's weakness. The weaker the gravitational attraction between objects, the farther apart they can be while still remaining bound. If gravity were stronger, galaxies would be more tightly packed, collisions between stars and planets would be more frequent, and the universe would be a much more chaotic and less stable environment. Gravity's gentle hand allows for the formation of vast cosmic structures, the intricate dance of planets around stars, and the very existence of life as we know it. It is in gravity's weakness that we find the conditions for a universe teeming with complexity and wonder. Section 5. Why so weak? Delving into the mysteries of gravity. The question of why gravity is so weak compared to the other fundamental forces remains one of the most profound mysteries in physics. Scientists have proposed several intriguing theories to explain this discrepancy, each offering a unique perspective on the nature of gravity. One possibility is that we don't experience the full strength of gravity. Imagine a tablecloth held taut at its corners. If you place a small object on the tablecloth, it will create a slight indentation. Now imagine a bowling ball placed on the same tablecloth. It will create a much larger indentation. Some physicists believe that gravity might work in a similar way. Just as the bowling ball creates a larger indentation, heavier objects might interact more strongly with gravity. This could mean that gravity is actually much stronger than we perceive it to be, but we only experience a fraction of its true strength because of the relatively small masses of objects in our everyday experience. Another intriguing possibility is that gravity leaks into extra spatial dimensions beyond the three spatial dimensions, length, width, and height, that we experience. If gravity were to propagate through these extra dimensions, it could explain why it appears so weak in our three-dimensional world. Section 6. Extra dimensions, a playground for gravity's strength. The idea of extra spatial dimensions, while mind-boggling, is a serious contender in theoretical physics. String theory, for example, suggests that the universe might have as many as 10 spatial dimensions, with the extra dimensions curled up or compactified at sizes too small for us to detect directly. If gravity is free to propagate through these extra dimensions, its strength would be diluted across a larger volume of space, making it appear weaker in our three-dimensional world. Imagine pouring a cup of water into a small sink. The water level would be relatively high. Now imagine pouring the same cup of water into a large swimming pool. The water level would be much lower. Similarly, if gravity is spread out across more dimensions, its force would be diluted, making it appear weaker in our three-dimensional experience. This concept offers a fascinating glimpse into the potential for hidden dimensions to shape the fundamental forces we observe. Section 7. Gravity as an emergent force. A new perspective on an old enigma. Another intriguing line of thought suggests that gravity might not be a fundamental force at all, but rather an emergent property arising from the behavior of more fundamental entities. Think of temperature, for example. Temperature is not an intrinsic property of individual atoms, but rather a macroscopic description of the average kinetic energy of a large collection of atoms. Similarly, some physicists believe that gravity might emerge from the collective behavior of microscopic degrees of freedom, much like temperature emerges from the motion of atoms. This entropic view of gravity proposes that gravity is not a force in the traditional sense, but rather a consequence of the tendency of systems to evolve towards states of higher entropy or disorder. While still in its early stages of development, the idea of gravity as an emergent force offers a radical departure from the traditional view of gravity as a fundamental interaction. It suggests that gravity might be a macroscopic manifestation of deeper, more fundamental principles yet to be fully understood. Section 8. The Quest for Unification, a Symphony of Forces. The search for a unified theory of physics, one that seamlessly weaves together all four fundamental forces, is a driving force in modern physics. Physicists have long dreamed of a single, elegant framework that could explain the universe at its most fundamental level, from the smallest subatomic particles to the largest cosmic structures. Unifying gravity with the other forces, however, has proven to be a formidable challenge. The Standard Model of Particle Physics, our best current description of the quantum world, successfully incorporates the strong, weak, and electromagnetic forces, but leaves gravity out of the picture. String theory, with its extra dimensions and vibrating strings, offers a promising avenue for unifying gravity with the other forces. However, string theory remains a highly complex and mathematically demanding framework, and experimental verification of its predictions remains a significant challenge. Section 9. The Enduring Enigma. Gravity's Weakness and the Future of Physics. Gravity, the force that shapes the cosmos and guides the dance of celestial objects, remains one of the most profound enigmas in physics. Its weakness, far from being a limitation, is a testament to the intricate balance of forces that makes the universe a hospitable place for life. As we continue to explore the universe at its most fundamental levels, the mystery of gravity's weakness will undoubtedly continue to captivate and inspire physicists for generations to come. The quest to unify gravity with the other forces, to unravel the true nature of this fundamental interaction, lies at the forefront of our journey to understand the universe and our place within it. The weakness of gravity, once a puzzle, is now recognized as a key to the cosmos's grand design. It is a reminder that the universe's most profound truths often lie hidden in plain sight, waiting to be uncovered by those who dare to ask the right questions and seek answers in the vast expanse of the cosmos.